Hey you guys, I thought I would quick make you a little video about the discussion that you guys just did about calculating the thickness of a piece of like a sheet of metal. And the reason I came up with this little discussion was really just about how to visualize chemistry. And chemistry is all about atoms, and it's about what things are made of and then how they're changing, hence the chemical changes that you might see on a piece of metal. And it's also about dimensional analysis, and dimensional analysis is just keeping track of the units on numbers and then how you can manipulate those numbers to your advantage when you're trying to determine something new about a set of materials or a procedure or process. So for this discussion, what you had to do was look at your piece of metal, and then you had to claim it first, which you did, and then use the information that was given. And in exploration number 1, that was kind of a review of this, but with no talking, to calculate the thickness of the piece of metal. So the information that you were given about your piece of metal was the mass, and that mass was written on there, and then the dimensions. And the dimensions for this piece was 4 15/16 inches times 1 inch. So when we wanted to look at that, we could just now, first thing we have to think about is, well, what does that even mean? 4 15/16 of an inch, that is, can be transferred into a decimal. And when we look at this and we want to think about how thick this piece of metal is, if you look at your piece of metal at the top here, your piece of metal at the top has a length and it will have a width. And this thickness that I'm talking about is just right here. I mean, it's so tiny that it really can't be measured with a ruler or any type of measuring device such as that, but we can calculate what it has to be based upon parameters of that piece of metal. And that piece of metal has a length and a width. So we can say, okay, we have a length and a width. What do I do with that? Well, first off, how many significant figures does that have? And this is kind of interesting because significant figures are a reflection of the measuring device. Well, the measuring device here was a ruler that could read to the 16ths of an inch. And that 16ths of an inch is a fraction. And when you take it to a decimal, it gives you, looks like, 5 significant figures or 4 digits after the decimal, and that's pretty good. Now, this next one you have here is just 1 inch. You think, well, that doesn't give you very many significant figures. But when you think about if it's the same ruler, that means if you convert that to a decimal, it should basically have, the same number of decimals after that first number. So that would be that. So when we think about what am I going to do with this? Well, we're trying to figure out the thickness of this piece of metal. So if we know we have a length and a width, can I possibly calculate the area and then relate that to volume? And that's what we're going to do next here. So what we're doing first is calculating the area. The area is a length times a width. And when I do that, I really should have had 0.0000, right? And then that's why I keep all the significant figures in my multiplication. When you multiply numbers, you choose the number with the least number of significant digits to round it to. But in this case, we don't have to. I should have had 1.0000 because it was with the same ruler. So I left all those significant figures in the area calculation. So if we remember that that volume is length times width times height, and we have a length and a width. You see it right here. We have a length and a width already. We can use something. I feel like we're on our way to getting something, right? We have volume equals length times width. So times height. So let's see what other information we had though. We had density. We can know density about any metal or substance that we know what it is. We know it's copper. So we could have went out and looked up density. But we know density is mass divided by volume. But do we have the mass? Yes, we do. But the mass is in grams. The mass we were given up, it was in kilograms. Now that was on purpose, because it was on purpose because we wanted to kind of make you think about what units do I need to convert to. So that's what we needed to convert to. We needed to convert from kilograms, right, to grams. And that's what was done right here. That is a conversion factor. So when you use a conversion factor, don't worry about the number of significant figures. because a conversion factor has what's called an infinite number of significant figures. It's not, it's because it's not from a measurement. It's a conversion. You're just taking it from one unit to the next. Now we know that density equals mass divided by volume. So now that I have the mass and I have density, but you'll notice I don't really have volume yet, but I can get volume, I think, right? From that calculation you see in front of you. This is now the volume of that piece of metal. Now you think that it does have a volume. Anything has a volume, right? If it's three-dimensional. So that's what we've done there. So finally, if you look right up here, what are we doing next? I just said the area, I couldn't use that volume because the volume was given cubic centimeters. My area was given square inches. So I need to take that square inches and I need to convert it to square centimeters. And then I'll be able to use it to my advantage because I see that I have cubic centimeters. I see I have cubic square centimeters. And if I do some mathematical manipulation on that, I could get centimeters. So that's the reason I'm jumping all over the place and looking at all this stuff, trying to put it together. So on our next, I've gone to the next slide. It looks very similar, but I took away all that stuff that we worked on so far, kind of focusing on what we need to finish this up. Are those two values. We have a square centimeter and we have a cubic centimeter. So if I then do a division, I can get centimeters. So that's what I did here. I took this number, 31.855, and I divided it into 0.3183 cubic centimeters. And when you do that, I take a cubic centimeter and I divide a square centimeter, and I end up with just centimeter to the first. So if you remember your algebra, when you divide exponents, like something like x cubed and x squared, you are subtracting. So that's where that 1 comes from. But now let's think about significant figures. Can I have all these significant figures? Probably not. I have to now do some rounding. So I'm going to round. I am going to round this height, and I'm going to round it to how many significant figures? Probably 4, right? See, this has 4 significant figures. So I'm going to round that, and it's going to be height is equal to 0.009992 centimeters. And if I want to play around and put that in scientific notation, it would be 9.992 times 10 to the minus third centimeters. And sure enough, that is super thin, and I wouldn't have been able to measure that with a ruler. Now on to the rest of the discussion. We're talking about chemical changes. Chemical changes are something that happens to a substance that changes who it is, what it is. So when you look at this piece of metal up here, you might see some changes here. Now copper does this very easily and nicely. Most of the metals in this discussion, you didn't see a lot of changes, and that's why I thought, well, let's just go look up what it would be if it did change. So Wikipedia is your friend. I mean, people might say Wikipedia is not the greatest source, but at this stage of the game, I think it is a pretty good source. And if you're worried about its accuracy, then you can look at these different references that it has about what you're reading about. So copper, you could just start reading about copper. What's fun about this discussion? You just come up with some fun things for somebody else to read about copper that they might not have known. So I go to Wikipedia and I'll notice down here, see, it's got chemical properties. I can go look at that. And when I do, this is what I find. You find some neat pictures in here about copper having some chemical changes, making it turn green over time. What these different things mean. Of course, you might hear about the Statue of Liberty, or this word verdigris. I think it's a French word, which means copper carbonate, because copper can react with carbon dioxide in the air. It can react with oxygen in the air. I don't know if it reacts with nitrogen. I don't think it does, but you could pretend. And you can say, oh, maybe it does. It can react with sulfur compounds to make copper sulfide. So these are all things that you could go look up about copper and write some chemical reactions that would illustrate that. The physical appearance of the piece of metal. Now in this example, you had some changes there. Is that chemical changes or physical changes? The idea here is to get you to think about those things. What is a physical change? What is a chemical change, and how can it be represented? So that's where I ask you to write the chemical equation that represents those changes. Of course, you could be looking at Wikipedia and say, oh, copper metal, solid, reacts with oxygen in the air to make a copper oxide. Now it can be copper, what's called copper 2 oxide. This is a solid, or it could be copper 1 oxide. Then there's different formulas that represent that. This is just getting you to think about chemistry and how to represent the changes that matter undergoes. I found this GIF on Wikipedia. Wikipedia is super fun to look at, and it's talking about this. This is melting of copper and the colors that it can exhibit. So that's a molten piece of copper there. So that is copper solid being converted to copper liquid. That is a physical change. And this, what's interesting I learned on Wikipedia, is that the density of solid copper is this. The density of liquid copper is this. See, so it changed. And cubic centimeters and milliliters are the same thing, but the density actually went down. So the atoms started to spread away from each other, which kind of makes sense because it's getting hot. Another part of this discussion was looking at, since we're in chemistry, we want to think about atoms and thinking about the size of atoms and how small or large they are compared to our macroscopic view. So the idea here was to look at the length of your piece of metal and say how many coppers are actually lined up in there. Well, to figure that out, you would have to know the size of a copper atom. Again, Wikipedia. There's a radius given over here. Now, a radius of an atom is half, right? You would want to know the diameter of the atom. Now, you might notice the unit, and the unit is picometers, and a picometer is really super small, and the conversion for a picometer and a meter, in 1 meter, there are 10 to the 12th picometers. Now, I can flip that and say on the flip side, 1 picometer is a 10 to the negative 12th of a meter. It doesn't really matter, but either way, that would be your conversion between meters and picometers. Now, centimeters, on the other hand, 1 centimeter is equal to 10 to the minus second of a meter. So you can see then, if you're comparing meters and picometers, or picometers and centimeters, there's some things you might want to think about there. So let's see if I have a quick conversion here of this. So here you can see that you have inches, and then you have, we did this inches in the beginning. We converted it to a decimal, but now I'm going to convert it to centimeters so I can convert it to picometers. This is how many picometers long my piece of metal is, and of course it's a huge number. But then when I want to do the conversion of how many copper atoms are in there, you see I take the complete length of my piece divided by the diameter of my atoms, and I get this many atoms. Well, this brings up an interesting point here, because we can't have a fraction of an atom. It doesn't make any sense, because an atom is like it's a unit. You can't cut it into slices. So then I ask you to put it in scientific notation and round it to the correct number of significant figures. You can see that right here. I've rounded it to 3 sig figs. I guess I could have left it 4, but maybe not, because my radius was given in 3 significant figures. So I needed to round it to that. So of course it's a lot of atoms. One more slide here. We're looking at the final part of this discussion, which was thinking about dimensional analysis again, and how I can just use dimensional analysis, which is this kind of converting from one unit to the next. And that's what I'm doing here. I'm taking the mass, as I said, start with the mass of your metal in grams. Oops, grams, but I started in kilograms, then convert to the thickness in centimeters. Now this should entail 5 steps, but it looks like since I started with kilograms here, I had to merge 2 steps, and I'll show you that here. So the first thing I did there was convert from kilograms to grams, and so what I can do there is I can cancel those units. The second thing I did there was use the density, and when I used the density, I was converting from grams to centimeters cubed, which was the volume. The next step I needed to do here, which is where I was talking about merging 2 steps, is that I needed to convert centimeters to inches. And the reason I needed to do that, remember, was because our dimensions were given in inches. So when you look at how I'm canceling things here, I had 2 inches on the denominators here, and then I had 2 inches on the numerator. This portion here is taking that centimeters, to centimeters to inches to centimeters, but You'll notice I have 2 of them, and now I have 3 of them. So at the end of my answer will be in centimeters. And this should match what I did in the very beginning, which it does. So you see there's different ways that you can play around with this dimensional analysis. The idea is to see numbers and see units and think about how you can manipulate them to get what you want. So I think that is finishing up with my little presentation on that the dimensional analysis discussion number 1. And hopefully you learned something from that, and then you can come back, and I think I might write a question for the final exam, you know, that you have to do something just like this. So if you go through and you think about stuff like this, do many different ones. And if you go through the discussion, you can see other people's answers and see how they did that. Okay.